This is roughly where we are on the program at the moment. I might just turn this around so I don't trip on things. There's me and Carol, and you get to have a bit of coffee. We've had lots of nice high-level overview talks, and it's now time to come thumping back down to the dirty reality of what actually happens when you start to do an experiment and roll up the sleeves and talk about actual data analysis and where you start things off on. So, starting at the start of things, I'm going to talk a bit about what do you do to actually reduce and pre-process your data to get some rapid feedback and some idea of what's going on, and reduce the data to something that you can put in your suitcase and maybe take home, or at least FTP home by the end of the experiment. It's not particularly sexy, you know, integration, indexing, all that stuff's much, much more interesting in many ways, but it's kind of a necessary evil because it takes you from data that's fairly large, data sets that are fairly large and unwieldy in strange formats into something that you can actually poke a stick at and start to do real analysis on in a reasonably efficient manner. So if you don't mind me asking a question here, how many people have actually been and done an FEL experiment at LCLS? Who's, hey, that's great. So a lot of you know what's going on. Who's not done that at all? Okay, actually, okay. So there's a couple of people who have not actually done it, which means I need to include a couple of the slides of the dirty work of what actually goes on. A lot of what I'm going to talk about is described in this paper, which is fairly boring. It's part of the literature there. So this is where you sit. You go to LCLS to do an experiment. This is the coherent X-ray imaging beamline, all decked out in red. And the X-rays come in this direction. The end station is located about 370 meters from the source, from the undulators where the lasing actually happens. And it's pretty amazing to sit there and look down the beam pipe. There's two experimental chambers. One up the front here, which uses small focusing optics, produces about a 0.1 to 0.2 micron spot, and has a focal length of about so much. And then there's another set of mirrors, Kirkpatrick-Bayes mirrors, that produce a focus in the far experimental chamber here, about 1 micron in size, and a set of detectors and everything. And this is the sample delivery. Uwe Weisstahl here working on one of our earlier experiments with the sample delivery. You've got a large rod on the center there. That's just a mechanical way. It's like a lance. You just put it in, and it has one of these tips on the end of it that enable you to deliver your sample into the X-ray focus. And down a little bit further are the detectors and everything. What you do, you fire all that up, and then you sit in this little dungeon here, and you start to collect data. And you notice a couple of things that, as John mentioned, are really different with your with things that are coming in. One is that the spectrum and the shots are fluctuating seriously from shot to shot. So the control freak experimentalist at a synchrotron tries to have the most stable beam, the most stable wavelength, the most stable goniometer, the best everything to control all the experimental conditions as much as possible, so that the only thing that is changing is the crystal orientation, and this enables you to do very nice error analysis and very nice analysis of the data. At the FEL, each shot is a statistical process, and if you operate in SASY mode, which is what most people have been doing, you get this rough, spiky spectrum that comes out. If you choose to talk to the machine physics people group about their latest work, you can go in seeding mode. It's basically like putting a monochromator in it, but then you can get a very nicely well-defined wavelength coming out of the system. A trade-off with that, the intensity is fluctuating a lot from shot to shot. So now you have intensity fluctuations. Your wavelength is well defined, but you have huge intensity fluctuations. So that will come into aspects of the data analysis and integration later on. There's the sample delivery, as has been talked about. This means that your crystals are in the random orientation and that you have something like a hit rate. So this is not one long crystal just being dragged through the beam like a fibre. It's a suspension of crystals, and these crystals interact with something that's like an X-ray focus. And a lot of the time you might just get solution scattering. Depending on the concentration of your crystals, there might not actually be anything crystal diffraction-wise in there at all. every now and then you get a crystal that intersects with the X-ray beam. Because this is continually flowing, it's completely random where the crystals are. You have a regular firing here. So whether or not you actually have a crystal in the beam is completely random, as well as its orientation. That means that you have something that we call a hit rate. So you don't typically, on every shot, get diffraction from a crystal. If you make this super concentrated and use the large focus, you can get something like a 50% hit rate. There'll be a significant fraction of double crystals in that, actually. If you've got a particularly bad protein, or the filtering wasn't good, or the jet's not so good, you might get a 0.1% hit rate, or 1% hit rate. That means that of all of the data frames that you're collecting, 1% of them actually contain something that's useful. So the first thing you think is, well, okay, let's just throw away the frames with nothing in it. You know, why are we even saving these things? And that's part of what this pre-processing step does, okay. It says, let's quickly look through the data and see which ones have plausible crystal diffraction that I want, and let's keep only those frames and take those home and do the subsequent analysis on it. You try to do that moderately quickly so that as soon as possible you get rid of all the frames that don't have anything interesting in it, and then you invest your time in the ones that actually do. There's no point trying to do crystal indexing on something without Bragg peaks. Okay. So that's one of the things with the pre-processing. The other thing is you have detectors that have come a long, long way in the past years. I would venture to say actually that we're almost beta testers for these detectors. This is a cutaway of the CS-PAD detector. It's the detector at CXI at the moment. It was developed for LCLS because of the unique properties of the X-rays. You can't use something like a Pilatus detector. The Pilatus counts individual photons as they come. If all your photons come in the space of 10 femtoseconds, you can't count them. You've got to have a bucket that integrates the charge with how many photons came in my 10 femtoseconds, and then leisurely reads it out afterwards. So these consist of a silicon front sensor element. It's aluminized on the front to keep visible light out. Silicon front sensor element, and underneath, immediately below that, is a set of specific circuits. Behind each pixel is an amplifier circuit that amplifies the charge and digitizes and gives a readout in 120 frames a second and reads out all these things. So these were developed for LCLS, and over the course of the past 3 years, they've come a long, long way, but some of the early experiments turned out to be pretty tricky to analyze because of detector artifacts that now, over time, as things have been developed, have got a lot better. So actually understanding a lot about the detector and its limitations is fairly critical too, because it's not quite as well controlled as what you get on a synchrotron. And then, hello, are you going to even talk to me here? Okay. And then the other thing we're going to spend most of the time is data handling and data things. As mentioned, you get lots and lots of data. In our first experiment, I wandered down the hall and found a rack with 288 hard drives, and I thought that was impressive. And these days, there must be at least 1,000 hard drives wandering around LCLS, if not more, because I think there's 6 petabytes of data floating around or something like that, and storing this stuff and managing it and crunching through it is not for the faint of heart, and it's not something that your average research group can really undertake. You know, if you're on a university research budget or at a small institution, going out and buying that quantity of hardware will probably sink your 3-year research budget. So we pretty rapidly realized that if we want to make this technique accessible to the widest range of research groups and the widest range of researchers, then we needed to do something pretty quickly to mean that people didn't have to deal with these huge volumes of data, but could instead shrink it down into something that was manageable pretty quickly, and then take that reduced data home as well. To give you some idea, a petabyte disk drive will cost you of the order of $200,000, and is serious enterprise class stuff that you don't get down the street. If you want 100 terabytes, you can get a nice array from Dell, probably purchase order from your department. And if you can reduce the data down to something like 10 terabytes these days, you can hop in a car, go down to Fry's, and get enough hard drives to actually do it. Okay, so by shrinking down the data volumes and shrinking down the computational requirements, you actually make the technique available to a wider range of people and then push things as well. So that's one of the things we did there. Okay, so why is it an issue? You got this beast. It's an X-ray source pulsing at 120 frames a second, and on every frame you read out your detector and you save it. There's no real logic on the detector to say keep this frame or not. What it does is it says I've got data, saves it, pushes it down through the system. So you're getting 500,000 frames per hour, or about 5 million frames per shift of data. Not all of it means something, but that's how much data is coming off the detector, and it's a fairly, at least when it started up, a fairly heroic effort to get this data off the detectors and actually put it somewhere to do something, okay? So 4.5 megabytes a frame, you've got about half a gigabyte a second going out, or 1.8 terabytes an hour of data that you have to process in real time and move along copying without a glitch, because if you have a glitch or you mush up the data or you do things, you're going to totally screw up the analysis. So 1.8 terabytes an hour, and if you add up the amount of beam time, you're rapidly going to get into the tens of terabytes, and an experiment can easily be, typical experiments for 5 by 12 hour shifts. We'd go home with 26 million images and 110 terabytes per detector. Sometimes we're running 2 detectors, but your detector doesn't run, you have experiment downtime. So we have taken home, I think, from one of our longer experiments, 140 terabytes of data. Which is fairly intimidating, and you fairly quickly buy large hard drives to deal with that. The data rate was such that when you stream data off these detectors in order to process it, you can't send it through just one pipe. It turns out that what Slack does is it multicasts the events across many server nodes, many analysis nodes. So it's sort of like dividing things up amongst multiple lanes on a freeway. You say one car here, next lane, next lane, next lane, next lane. Each machine doing the processing and event aggregation can only operate so fast, so you do it in parallel and you switch the events between things. What does this mean? It means when you go and ls your directory, you end up for each individual run with different server nodes, and then to make the files not too big, different chunk sizes. So you've got your data is not just one file, your events interleave between these files, so it'll be one event here, then the next event is in this file, and the next event is in this file, then the next event is in this file, cycling between these things. Goes from these servers through the online analysis nodes where you can do some preliminary analysis on the fly. If you crash these nodes, you're in trouble. Onto a fast feedback buffer. It's a huge RAID drive of solid-state disks where you can look at the data really quickly. And from there, it is migrated over onto the mass storage of spinning disks, eventually archived to tape for 10 years. Okay. And it's these files here, they're not too big. They're only of the order of 100 gig each per file. And each file, of course, contains multiple events within it. So you're sitting there, here's the challenge. You're sitting there as a newbie to FEL data analysis, and the beamline scientists are magically clicking things away, and they're doing their stuff. And they say, okay, let's look at my data. Where is it? Oh, it's in this directory. Here, what's this? What? Usually people come out with the following types of questions. Where is my data? Because it's existing somewhere in the ether. What the hell is an XTC? My, XDS doesn't open it. What do I do now? How do I take 100 terabytes home? Okay, what am I going to do? How do I read an XTC anyhow? And that's when you talk to Chris so great. Of course, LCLS has its CAN openers, but then it's like finding a bunch of tools on the desk and you've got to figure out what to do. What do you do now? Okay. So that's what we tried to address, this problem of, shit, what do you do with your data when you come home? So our approach to this has been to do basically massive data reduction up front. We got your detector, it goes onto storage, LCLS takes that, and for a given sample you might have something like 4 million frames there. Then what you do is you run a pre-processing step on it in which you do identify only the frames that have hits in it, only the frames that have crystal diffraction. So now I'm just talking about what we're talking about here, serial crystallography. This data is stored uncorrected, which is great because it means that if there's a stuff up in your calibration, you can go back and fix it later. But down here, for the analysis, you want all those corrections applied. So not only do we do the hit finding, we know where the bad pixels are, we know what the common mode offsets are, we know when 2 gain modes were used and apply the corrections for that, and spit out, as part of this offline reduction, as much detector correction as possible, knowing where the bad pixels were. so that when you get down to Tom and Nick's software here with the indexing and integration, you have something that looks like, here's a bunch of detector-corrected data containing only the crystal diffraction, and I'm going to work on this to understand my software. Because of the data volumes and all of these files, high-volume processing is essential with all the background corrections and everything applied. 4 million frames, 400,000 hits, that's like a super saturated solution of lysozyme will do that, it'll be really nice. We have actually got structures nicely out of, we ran for roughly that length of time, but it was a really, really nasty GPCR, got 10,000 hits and maybe 8,000 index patterns, and you can still do molecular replacement with it at that sort of a level. So here, 4 million frames to this, you're doing a 10% reduction. Here, you're doing over a factor of 100 reduction in the amount of data and then the amount of subsequent processing that needs to be done. So going back to that bar, no, I didn't want to go all the way up there. I did not want to do that. Sorry, back button got a bit carried away. The tyranny of transitions. Now you've got all of these things. The way the experimental people at LCLS run it, they sit in front of this control screen, and there's what the finest granularity you sort of have is something called, in practice, something called a run. There's a button there that says, start recording the experiment now, and it records it faithfully like a tape deck, all the data to disk, and then stop recording. Start, stop, and please save this. Those are called runs. To save yourself drowning in data, create a Google spreadsheet. Nadia's got some for these experiments. Basically, for this experiment, run number what, when was it, so you can always look up someone else's notebook, if you've got a manual notebook or something like that. What was in it, who owns the sample, comments, what was the beamline transmission, this, that, and the other. You just, in practical terms, chunk your data into runs whenever your experimental conditions change. Dark run here. This was meant to be catepsin B, but someone accidentally loaded water. Okay, won't find any hits in there. And so on. So that's the first level of organisation. Okay, the finest level of granularity, record what is in each run. Simple enough. But that helps. And then as for the hit finding, and now I get into what, that's sort of what Cheetah's doing. So you fire up Cheetah, it's used for the data reduction, and it comes up with a control panel interface like this, where each run is listed. You can provide here in a tabular form how many are processed, how many hits were found, and the rough hit rate for each run, just as a simple way of summarising things. It does the data reduction, so it only keeps the frames that have crystal diffraction in it. It translates it into a facility-independent HDF5 format. So Tom, thankfully, doesn't have to deal with XTC formats. He just has to deal with the HDF5 format, which is a portable library. If you want to analyse your data at home or somewhere else, you do not have to translate or port an XTC reader. You just need a HDF5 reader. All of that mess is dealt with by Cheetah, and it sort of provides a top-level organisation. So if you process everything with the same conditions, with the same ini file, it'll tag it for you, and everything will be in the sort of sorted out. Newly collected runs. As you collect new data, it appears here, and it comes up that it's ready for analysis. What's the status of data collection? So you can be sitting upstairs in the analysis room. Oh, 3 new runs have just come in and been collected. Let's process those. Let's check what was in the Google spreadsheet. Yes, I should analyse these using the following script. Click a button, and you start the processing. And then as it's processing, it's tagged what it is, which directory it's going into, the status of processing, the number of processed runs, updated about every minute, how many hits it's found. Okay? So what does my data look like? Powder pattern. Okay, you click on one of these lines and say, show me a virtual powder pattern. This is the sum of all the Bragg peaks that were found. And it gives you just some idea of, does the powder pattern look like crystal diffraction, and what resolution does it extend out to? What's my hit rate? It's processing through the data, so you can just plot a simple graph of what was my hit rate doing. Obviously something was not so good here. Then it got a bit better later on. Okay? That's very useful for the people mixing up concentrations and downstairs, because what you see on screen is images flashing by and you can get a gut feeling, but actually having a plot of the hit rate and how things are going is pretty good. Okay? What's my resolution? So it all boils down to finding Bragg peaks, and you can say 80% what I do, just to avoid getting confused by one outlier that's going to screw things up, what's the circle that contains 80% of the found Bragg peaks, and plot a histogram of it. So in this case, it was a nice sample. They're diffracting out to about 700 pixels on the detector. So you know that that was a reasonably good sample. You can also sometimes get quite different distributions. It gives you some idea of, on aggregate, what's my diffraction looking like. This is a useful one, it turns out, saturation. The CS pad detector has a maximum full well capacity of about 2,500 photons, and it's very easy, you know, Wilson B factors exist for a reason, and it's very easy if you want to detect your high resolution peaks out here to saturate the detector at low resolution. If you saturate the detector at low resolution, you know that the intensity was above some value, but you don't have any idea of what it is. So on a CCD device, if you fill up one well, the charge spills over into the neighbouring wells, and you can actually integrate it to still get the total amount of photon energy deposited in there. With the way the CS pad has got very steep sides to the wells, you fill it up, and what happens is it just says, it was more than this. I've saturated. I don't know how big it actually is. That, of course, ends up causing problems for the analysis, because if you run it to get your high resolution peaks out here and you have nothing but saturated peaks at low resolution, this is going to affect your data analysis. So it's very useful to be able to quickly say, is my beamline attenuation good enough that I'm actually getting reasonable measurements at low Q and at high Q? And you can just plot up a saturation plot here. So usually saturates, this is 20,000 counts, about 16,000 counts is where it normally saturates. And in this case, we're running dual gain mode, because the CS pad can run in a mode where you can per pixel, say, run in high gain mode or low gain mode. And what we've done is, on this side, run in low gain mode, which means you effectively get more dynamic range up to about 60,000 counts. You can still saturate, of course, that bit. But that means that rather than being clipped at this level here, we've been able to extend the dynamics. And those corrections have all been factored in. But it's a very useful way of being able to see, are we getting too many saturated peaks or not? You know, there's a bunch of other stuff that goes on as well, like we've done pump laser on and off, and you want to then, of course, sort by here the ones with the pump laser on, here the ones with the pump laser off. So you write into Cheetah a little bit of a sorting thing according to some criterion that creates two piles of data that you can then analyse separately. Just basically two file lists, just says these are the ones with the laser on, these with the ones with the laser off. Or you can write your own sorting routine there. We've used it for other experiments as well. This was, John talked about Richard Neutz's wax analysis. We basically did radial profiles for every shot and outlier rejection normalization. And this is every frame has its individual radial profile, and then you can go through and do statistical analysis on that. Same with the spectrum, shot to shot. See what's happening on the spectrum, shot to shot. And for single particle analysis, you can actually take this detector of 2 million pixels and do a histogram of the values, of the detector values on every shot, and do up a histogram. So that's a single photon peak from a dark field in a single dark field thing. So that's the dark counts with its natural width, and that's the single photon peak, and the difference between those is the number of ADU per photon, per pixel. So you can actually calculate that value on a per pixel basis. And then one of the most useful things, of course, is crystallographers have a good intuitive feel of what a good diffraction pattern looks like, and the first thing they want to do is, what does my data look like? So you click on the button up there, view hits, pulls up a separate viewer, circles the Bragg peaks that were found so you can see what the Bragg peak finding is like, and you just click through one image per second and look at 100, 200 images, and you get a rough idea of a feeling of what your crystals are actually diffracting like. Just shows you the hits. And you can sort of put it on a play mode, and it just sits there in the background, and you can sit there and watch sort of what your hits are like, and you can stop on one, look at it, decide to analyse it in a bit more detail, and just sort of very quickly get an idea of what your data is. So it's like, you see the hits flashing past very quickly on the DAC computer, and you want to go, I wanted to look at that one. Here you can sit back and look in a bit more leisure of what's actually going on. That actually turns out to be really useful, and there's no substitute for looking at your data. So spend a lot of time looking at this. And of course, the hit finding, as you can see, these are the found Bragg peaks. The way Cheetah works for this serial crystallography is it basically says, give me a rough estimate of where the Bragg peaks are, okay? do some quick and dirty peak finding. Tell me if there's more than so and so many peaks in here, and if so, call it a hit. So it all comes down to this messy business of peak finding. This is my current favourite algorithm. What it does is it calculates the radial signal to noise. So there's a function of radius that goes around in a circle. It calculates what the DC offset is and what the sigma is. So here, the sigma is not too bad, but when you get into the water ring, it's a bit higher. And then it creates a radially dependent threshold that's dependent on what signal to noise threshold you want. A peak is anything that's n connected pixels above that radially dependent threshold. And it just goes through and defines how many peaks there are of that, and more than n peaks, it's called a hit. So what you do is you end up spending a bit of time just tweaking that manually. Obviously, if you want weaker peaks, you need more pixels, or else you get too many false positives. So you just have to tweak those couple of parameters by hand. We'll get into that tomorrow. There's no substitute for manually verifying your peak finding, looking at it. Those of you who've written your own auto-indexing software will, and hopefully that's most of you because it's really educational to know how it actually works. When you want to index your pattern, you essentially take these found peaks and you project them onto reciprocal lattice vectors and look where there's the most periodic repeat. So finding correct Bragg peaks, and only good Bragg peaks, is critical to getting the auto-indexing to work. If you suddenly end up with nasty non-peaks in here, it's going to try and index those, and there's a greater likelihood that things won't work. So getting your peak finding right is good for both hit finding and then ultimately for the indexing as well. Okay. Getting an automated peak finding routine to work and going over that is one of the key things to getting the most out of your data, boring though it is. The other thing, for those of you who've written, for the majority of you who've written your own auto-indexing software, when you project these onto these reciprocal lattices, it really matters where these detectors are located. Okay. So now we get into the curly aspect of geometry. Because the detector is put together like this. Each of these elements is lithographically fabricated. You can trust where the pixels are relative to each other on each of these. But every now and then we kill them. Every now and then they're replaced. These are just put into sockets. And even better, these quadrants here can move. And there's a supervisor knob where you can change the gap and change the detector positions. And this changes the relative location of all of these ASICs. And knowing where those things are in space is pretty important. Here's this plot again. We've got a central hole down the middle where the direct beam goes through, and that gap can be changed. These quadrants can shift relative to each other so that things, and that means these four leaves can change position with respect to each other. Every time they change position with respect to each other, you've got to figure out the geometry again, or your auto-indexing isn't going to work. You've got your photon sensor, it's bonded onto these bits here. So each of these ASICs, you can pretty much trust where the pixel locations are. But from rebuild to rebuild, each of those might be slightly different, and especially when you can translate these things around. I'm not going to go into the sample and hold amplifier back there. But one of the things that happens with this detector, when each of these electronic modules here, you just read out the data and dump it into a slab of memory. So when you look at the data, it's not neatly arranged into a 2D detector with all the geometry applied. It's just chunks of memory. It's like, here's one, 2 by 1, here's the next, and it's just in chunks of memory. You don't know where it is in space. It's not nicely assembled. You have to do that yourself. And you can do that if you want to look at it. But for analysis, it doesn't actually matter a damn. All you care, where are the peak locations on each sensor module. And then if you know the geometric specification of these, you can remap those pixels to wherever they're meant to be. And you also don't want to do interpolation of the data, if possible, because that might screw up your peak values. So what in practice we do is do the peak finding and integration on this sort of very low-level layout, not caring which way all of these are twisted around, and then apply the geometry just as a last step. Let me make that concrete. The data is sort of these 2 by 1s, and it's just in memory like this. You can see it's a powder pattern, but it's a bit like a jigsaw puzzle. If you want to make it accurate, you've got to apply the detector geometry. But when you actually want to do a radial average, let's say you wanted to do a radial average of this, you really only care what the radial position of each of these pixels is. So if you have a lookup table or something saying what's the radial position of each of these pixels, you can just go through this array and compute a radial average without ever having to do this. In the same way, if you know there's Bragg peaks in here, if you know there's Bragg peaks on pixel whatnot here, and then you have a specification for where this is in space, all you do in your software then is before sending it to MOSFilm, you say, remap to where these things are in space, and then do your auto-indexing for the geometry. So getting that right is fairly critical. What you end up doing is having a rough optical metrology, rough knowledge of where these things are. Then you, by hand, sort of align them to a powder pattern to get the rings to line up. And then the ultimate way to sort out your geometry is to compare the results of auto-indexing. Where's my found peak? Where did I find a peak? And where did the auto-indexer predict it should be? From that you can get the error in the location of each quadrant, or in the location of each ASIC actually. So here, if you compare the location just from using the online available optical metrology of where was each pixel to where it should be, and once you've done the indexing, this is basically the magnitude of the error between where the found peak was to where it was predicted by the indexing. You can see it goes up to 3 or 4 pixels error. And then you can use this to totally correct what the geometry is without having to reprocess your data and get it down to less than 1 pixel error. Okay? So using this comparison of indexing to found peaks, starting with the optical metrology, powder pattern alignment, and then refinement using indexing, you can get a good geometry. And that is the second big key to getting your data right. Because if you are predicting peaks in the wrong location, it's bad. And if you have the wrong geometry, you can't index the patterns to begin with. John?
The powder you're talking about there is a known structure, not your unknown. Is it a reference set?
It's nice to do it with a lysozyme or something with not too big a unit cell, but you can actually do it from the data itself in the end. You can actually re-refine on the data itself as you go along, but only once you're within a certain capture radius.
Can you incorporate reference data into Cheetah to calibrate, for example, your resolution scans in angstroms rather than pixels?
I mean, why do I do it that way? It's partly because we had problems with the detector encoders at some point, and if these things are not read out properly, you end up with really strange things. So it was easier just to do it in pixels at that point. Of course, you can put in a calibration, it's just a number. So I talk about damage to the detector. This is a not so enlightening event. It was sample being delivered, and you have ice growing up here. We moderately regularly destroy detectors, it turns out, through mistakes like this. So here's an example of what it's like when you're shooting that. You get these huge Bragg peaks from the ice. This was one of our first experiments showing how you can inadvertently damage the detector. And we actually took a pot shot on the power distribution board circuit of this one and took out the whole ASIC for the rest of the experiment. It no longer worked, just as a result of an ice shot. If I run that again, so this is what happens when you're running ice like that. You get these huge intensities that overload things, and then you can even destroy whole ASICs doing this. Periodically, we've come to do an experiment, and there's been sheepish words. The last group shot a laser at the detector by mistake, and now these two are not working, and the offset on that is wrong, and all sorts of things. Because if you add up just crystal diffraction, this is about 5 hours of data collection, and if you just sum it all up, you get about 10 to the 8th ADU per pixel. Okay, but if you run 35 seconds of ice, you get pretty close to the same value. And what you find is your beamline scientists, the minute they see this, they throw the stoppers in, put the attenuation in, turn it down to less than the flux of a synchrotron, and before you know long, you've got a wimping along experiment. One of the consequences of this is that bad pixels come and grow. In this same experiment, this was the bad pixels on every run as we went through the experiment. So by the end of the experiment, we'd nicely burnt in bad pixels into the detector over the course of it. And one thing Cheetah learned to do was to find bad pixels as they came along and identify them on the fly, and stick all of this metadata, this useful metadata, into a HDF5 file. Now, for those of you who don't know HDF5, it's basically like a file system within a file system. It's a bit like a zip file, maybe you could think of it. So it's a data format, and within it you have these fields that are named, and you can include lots of different metadata in here. one of the things I do is put in the peaks that I've found, so you can use them for indexing. I put in the bagged peaks that have been found. So, for example, those burnt-in ice marks, I start saying, this pixel's bad, don't integrate data here. This is a hot pixel, don't integrate data here. This pixel looks stuck. This region of the detector is bad. You can put all of that into Cheetah. It's encapsulated in the HDF5 file as metadata, and you can pass it on to CRISPR to say, don't integrate this bit of the detector because it's dodgy in some way. CXIDB is one way to share data. If you want to get it home, I use this all the time. SCP works slowly. This is a nice streaming thing. It's got a web interface. Slack is a portal. And you can just go on the web. Take this data from here to there. Take it home, please. I've started something going at breakfast, and by the time I got to the airport at lunchtime, my 4 terabytes of data were already in Hamburg, Germany. Okay? It's a very practical way to get large data sets home. Cheetah is, we've used it at SACO, ESRF, and Petra. The reason we're able to do that is we had a modular design to the thing. Everything inside Cheetah itself is facility independent. We started off with the tendrils of the Slack frameworks reaching all the way down into our software. And then that framework ceased to be supported for whatever reason. Trends moved on, or it wasn't quite appropriate. We said move on to something else. And at that point, we realized that 2 things could happen. First, this software could be useful elsewhere. And secondly, we didn't want to be constantly chasing changing frameworks. So everything within our software is sort of our own domain. And the only thing that changes is event format translator at the start. So whenever the software is updated or a framework's changed, you just need to tweak this little file reader. It also means, for example, that Tom went to ESRF to process some data, and it took a couple of hours just to write a new translator and reader to be able to run Cheetah on the data collected at ESRF. And it also means that then the output format is the same. So the same HDF5 output format that I spit out at LCLS would be the same at any of these other facilities. So now CRISPR does not have to be completely rewritten for each facility. All of the functions in there, for those who want to program, they're just simple little functions that you could call on their own if you wanted to. There's Python wrappers if you wanted to do that. But don't worry, it's all pre-installed at Slack, and we'll get into more of that. So what do you get out the end? Hopefully, you get a nice set of reflection intensities. After indexing and merging all the intensities, I'd love to talk about this, but that's not the subject. This is basically Catexan B. It's the 150,000 index patterns, the intensity from those. Not the integrated reflection intensities, but the total intensity of the whole diffraction pattern, summed up in 3 dimensions, and then a slice taken through one of the reciprocal planes. So these are actually the 3-dimensional intensities around each of the reflections. That's what you want. These are the reflection intensities you want. That's in the other plane. If you take a look a little bit closer. This is like 150,000 diffraction patterns merged in 3D. And what you want to do is come away with nice measurements of these reflection intensities for your analysis. But that's the subject of something else. On bibliographies, I was pointed to this paper the other way. Tom and Carol pointed it in my direction. It contains a really nice discussion of CCTBX versus CRISPR. Actually, I read it on the plane, and it's a really nice reading. So that should be added to everyone's reading for this meeting, because it's actually got a really, really nice discussion in the back of it, and it's done really nicely. So what's it all about? Data reduction and rapid evaluation. Quickly evaluate your data, select and retain only the good events, and take home only the useful data for yourself. That's it. And before tomorrow, if tomorrow's to work, it'd be great if we could check this stuff out. Can you log on to PS Export? Can you see the data in our experiment? Can you write something there? Can you submit something to the batch queue? And can you access an IDS spreadsheet? Actually, I got an email this morning that says that this queue name might have changed and that this login might have changed. Yeah, so maybe we actually need to update that.
Yeah, maybe the first point is you're supposed to go into PS login.
Now, it used to be, yeah.
Right, that was supposed to be the case before. PS export was only for exporting data.
Yeah.
But that's starting to be enforced now.
Okay.
So PS login for the top number, and then the batch queue at the bottom is PSN CSQ.
Okay. There was a nice spreadsheet in the thing that I saw this morning. Okay, we should need to update that for tomorrow. Thanks.
So has everyone written down the spreadsheet address? Brett?
I presume you've got a link somewhere where you can do this stuff. It's just, if the tutorial is meant to function, we don't want to be fighting these issues in the first couple of minutes. Okay, it'd be nice to maybe over lunch sort out this stuff.
The data is available. The other things are easy to handle.
The question is, can everyone get it? Not that they're fighting it.
Hi.
Oh, hello.
What kind of vector corrections does Cheetah really do, or in detail do? Because I recently looked at the significantly positive reflections for large data set, that was one of the tutorial, and you can see inhomogeneities.
Yeah, everything, of course, can be turned on and off. So the answer to that question might actually depend on which processing was applied to that data set. The first thing that corrections that are applied is just the standard dark offsets from a dark run. And then we had several experiments where there were fluctuating values on each ASIC. Depending on the total intensity incident on one of those little electronic things, there would be a difference in the ramp to the analog to digital converter. And that should have been just a pedestal moving up and down, so we tried to estimate that pedestal and shift it round. We tried to estimate where the hot pixels and the bad pixels are in the data. So trying to shift that common mode offset around. In the previous versions of the CS pads, you had to estimate it. Now they have unbonded pixels that you can use to provide a slightly better estimate of that from version 1.6 of the CS pad. So that can be taken into account. And we used to do a local background subtraction over the whole image, just a moving window local background subtraction to try and flatten a lot of these artifacts and leave just the brag peaks. That ended up having some interesting feedback problems into the statistics and things. So we no longer actually do that. Even if we use it for the peak finding, we now output the data without that local background correction applied. But depending which data set you look in the CXIDB, it may be from when we used to do that data processing. So one of the things we did recently, for example, the CXI 22011 data set, the lysosome, Butte lysosome, was probably done using a lot of these rough and ready tricks back when that paper was published. The other month, we went back and reprocessed that using our current state of the art, and we can push the resolution to about 1.6 angstroms and index twice as many patterns and get much better statistics out of it, possibly because some of these things are now done a lot better. So we now actually with this radial peak finding thing don't need to do the local background subtraction. We don't save the data with the corrections because we've incorporated some of these things into the CRISPR peak finding, and we use the peaks found by Cheetah for the indexing a lot of the time, and then spit out the data with only the dark calibration subtracted and the common mode corrected and the bad pixels flagged. At the moment is the way we do it. But there are old data sets where we were a little bit more cavalier about things and then got a bit better as time went on. So that might have affected those values.